So in containers, it is something like it is going to remove one layer from the virtualization architecture, where instead of having the guest OS, my containerization platform allows my application to directly communicate to my host operating system. This is a very high level about the containerization concept. So imagine I have a .NET application. Will I be able to allow the .NET application to communicate to my host OS, which is Linux, in a direct method, but I will not be able to directly run a Windows container on my Linux host. So this is the difference between the virtualization and the containers. I'll come there. So the next thing I want to talk about is the technology behind it. How this containerization concept comes in. How I'm going to eliminate the guest OS and how I'm going to bring it. Okay. So this is where there is a breakthrough in the Linux kernel which came into picture. Okay. So to talk about Linux kernel, so Linux is an operating system which basically runs a kernel. On top of the kernel, you will be running some processes. Like for example, if it is you are installing Apache, so it will be running as a process. And if Apache spins up something, it will create child process and it will execute that by communicating to the kernel. The kernel will execute that on the CPU and memory and give the result back to the end user. Okay. So this is a process based, process oriented architecture in the Linux scenario. So uh, in Linux, you have a kernel and the kernel will be initiating a process. Okay. And that process, there will be a CPU and memory will be allocated for it. I think in the mid of 1990s, okay, there is a new concept called private kernel namespacing concept as brought into the Linux kernel. That means for a particular process, okay, you can allocate a separate area in the kernel. That means imagine you have a hall. There are 100 persons are using the hall. In the hall, you are just making a small block and only one person have access to the particular room. Okay, that kind of architecture they have brought in into the Linux kernel. That is where is the starter of this containerization concept. So for a particular process, I can allocate a private kernel space so that no other process will be able to come inside that process and see what the process is doing. So because of that, I was able to achieve a process isolation of the I can isolate the process from other process. This is one concept which enabled containerization. And the next concept is called C grouping. So C grouping is another Linux kernel concept where for a particular process, I can say you can use only up to one CPU. You can say you can use up to only maximum of 2 GB. Okay. So I was able to restrict the resource allocation for the particular process. Combining these two only, the containerization concept comes into picture, where the container, when I run a container on operating system, that container is going to run as a separate process and the kernel space of the particular process will be totally isolated. So no other process will be able to come and communicate to it. And then I can restrict the CPU and memory allocation for the particular process. Okay, so using these two concepts only, containerization concept comes in. So I have my containerization application. Whenever I run a container, it is going to allocate a private kernel namespace for me, and for that kernel namespace, I have a or restricted CPU and memory allocation so that I can achieve isolation and sharing of hardware in the same scenario. That is how the containers comes into picture. The first container comes into market is called LCX, that is Linux containers, which unfortunately which didn't become much popular. Then Docker comes into picture, which has become very popular, so that you are going to have a, as the Docker comes into picture, they have become very popular. And because of the Docker, I will be able to eliminate the guest operating system and I can allow my binaries to directly communicate to the host OS. So this is how it is going to look like. So previously the binaries has to communicate to the guest OS and talk to the host kernel. Here, the Docker layer in the middle is going to run the binary as a process directly on the host kernel. So this is the advantage or the technology behind the containers. when I talk about memory management and then CPU allocation, okay, so the kernel space, whatever it is allocated for the particular process, it may shrink or increase based on the need, but no other process will come into the memory space. The reason why I'm saying this is when you run a Docker container, okay, Docker thinks that, okay, it has all the CPU and memory for it, but it is not going to consume that until unless it is needed there. Like for example, I have a machine with 4 CPU and 4 GB RAM. Okay, my Docker container uses 1 CPU, let's say zero point 0.5 CPU and 1 GB RAM. Okay, so that space, until unless it is holding it, it will be with the process, that is the container process. If the container process releases that, that will be added to the central pool and other process can use it, but the data will not be there. Let's say I have a host. Let's say I have a hardware and I have a host OS, which is Linux, and I have my container platform installed on top of it. Okay. And when I run a Linux container, it is going to create a private kernel namespace in my host operating system. And from there, it will be communicating to the hardware and run it. Okay. But in this mission, I will not be able to run the Windows container because my Windows container will be giving instructions like a Windows kernel, but my Linux kernel will not be able to understand the Windows thing. Okay. To make that work, what normally people will do is, like if you want to run a Windows container on a Linux machine, this is the approach which is being followed, but I wouldn't suggest that because you are adding one more layer to it. So what happens is hardware, on top of that, you have your Linux OS and you have your container platform, and the Linux container directly communicates to it. But here, what happens is they will put a hypervisor like VirtualBox or some other tool. On top of that, they will install a Windows Gust OS. On top of that, they will be running the Windows container. Okay, so this is kind of a very lengthy, or you're adding one more layer of guest operating system and achieving this. But if you on a single machine you want to run both Windows and Linux containers, this is the only approach. But in the other way, if my underlying host operating system is Windows, I can run Windows containers. I don't have any problem in it. But I'll not be able to Linux containers on top of it. Okay, so Windows supports both containers modes. Like when you can install Docker on Windows, it can support both Linux mode and Windows mode. But the problem is you can run either Linux containers or Windows containers. So Docker on Windows use a concept called WSL. Okay, Windows for Linux something concept. Okay, so in that you can select whether I want to design this machine to run Linux containers or Windows containers. You can run either Linux or Windows. You cannot run both Windows and Linux containers at the same time. Okay, this is a limitation in the containers. Like the container OS and the underlying host OS should be of the same kernel. It's either can run Windows or Linux, not both at the same time. So this is the technology background of the containerization comes into picture. So on a high level, to compare, containers are nothing but a process. Okay, so that for that process I am creating isolation using the private kernel spacing concept, and also I'm limiting the resources using the CPU. Okay, so at the end, in the technology wise difference, so containers are nothing but a process with isolation and limitation. Okay, so as I have removed the guest operating system, the advantage I'm going to get in the containers are, first one, the resource utilized by my guest operating system, I'm going to save that. Like for example, if you take a Windows machine, the Windows operating system itself, it's take minimum of 1 CPU and 2 GB RAM for it. Okay, so I don't need that anymore because it's my application binary which is directly communicating to the underlying host. So I don't need the one CPU of 1 CPU and 2 GB of RAM for my OS, guest OS. And next thing is the storage which is being used by the virtual machine. Like for example, Windows means you just need 30 GB of space for the OS files and other stuffs. So that I'm going to avoid that. and I'm going to remove one layer of translation in the complete process. So I am going to get a better performance compared to the virtual machine. Okay. And the next advantage is, so if I want to bring up a service or if I want to do a deployment, okay. So after deployment, if I want to restart the server, let's say, so in the previous scenario, it will take at least 2 to 3 minutes for my application server to come up. And after that, my application has to be hosted. But in this case, it is just a process or it is just the binary. So just starting the binary, it's going to bring up the service in max of 30 seconds or 40 seconds max. So you will have a faster deployment with the containers. So you are going to save the unwanted hardware usage on the guest operating system, and you are going to have a faster deployment and faster startup cycle, and you will avoid, you will get a better performance in the containers. Yeah. Containers on the same OS kernel are lighter and smaller, better resources utilization, and boot up process is short and it takes few seconds. Okay. A typical example will be like in a virtual machine scenario, you see out of the total 16 GB RAM, the actual application is taking only 4 plus 3 plus 2, 9 GB. Okay. But the memory wasted are 7 GB on the operating system. But in the Docker scenario, the total memory used is 9 GB, the 7 GB is free for you. You can allocate new containers on top of it. Okay, this is one example. And startup, as I told you, you don't need to bring up the guest OS. So the application will come faster. Okay. And next advantage over this containers is the container architecture actually provide a API. Okay. So let me just talk about the Docker architecture. It provides a API. So as it is providing API, you will be able to communicate to the container daemon. Okay, we call it as a container daemon. So you'll be able to communicate to that using a programming interface. Okay, so you can automate things to it. Like you can talk, you can make Jenkins communicate to the Docker, and then it can bring up the containers and do this. And like that, as a designing a API, you can also write your custom code and communicate to the daemon, and you can proceed further on that. So this is the advantages of the containers. So it is lightweight, faster deployment, effective utilization of resources, and integration is going to be much easier as it is providing an API layer for it.